Good afternoon, everybody. Guess we're the last thing between you guys and happy hour, right? So we'll try not to keep you too long. I'm Dan Agnew. I'm with a company called EngSim. Varun is in the back. He's going to come up and finish a little bit of this presentation. We're going to talk about EVs today and how to do some computer modeling for them. Here's the PRI disclaimer. Can you read that in the back, right? You want me to read it too? Okay. All right. Okay, I'm going to start with an introduction and a background. Some of this stuff is pretty basic, so if you know it, just bear with us because we'll get to the good meat and potatoes stuff with the demo that Varun's going to show live if we can get our AV equipment running right. But I'm going to just very briefly talk about a profile of our company because a lot of you guys may not be familiar with us. Discuss why we do this kind of work, the tools that we're using for it, and then some of the EV basics, the nomenclature, and some of the major components. EngSim Company, we've been around since 2003. Those of us in the company, we've been doing this probably, if you added up all of our years of experience, it's probably 80 or 90 years of experience between us doing simulation and engine work as it relates back to that. We've been providing this modeling expertise in many technology domains for the engine and vehicle industry. OEs, tier ones, industrial, off-road, consumer products, and the performance industries. That's why we're here this week. For many clients, EngSim is their virtual engineering department, and that's pun intended there. A lot of our clients are large corporations, and we may just cover some of their overflow work or some special skills that they may not have in-house. And for other companies that may be too small to have their own engineering department or too small to keep the kind of tools that we use busy full-time, so we become their virtual engineering department also. Some of the technology domains that we work in related to engines, vehicles, electrification, and that's what we're going to talk about today, valve train, some thermal work, and then also 3D computational fluid dynamics. We do a lot of work in that. I was here last year. We talked about a CFD project that we did on a cylinder head intake port and an exhaust port. So our work is pretty diverse. But what we're going to focus on today is the center box there, the electrification. Motivation, why electric vehicles in the performance racing industry and why virtual simulations? Well, you can appreciate electric vehicles or not, but this industry and the major sanctioning bodies need to, and as I'm learning from this morning, continue to. There's a lot of sanctioning bodies already doing this. They need to embrace these to keep them relevant to the stakeholders. This is very important to the OEs because they're selling more and more EVs, and if the racing industry isn't bringing that up through them, then racing becomes less relevant to the OEs. And so the performance industry really needs to keep working on that and keep growing it. The tools and the methods that we're going to show here today allow those investigations to be done early on. And that really helps to determine the best path forward for EVs in the product industry. Oh, you got the converter. Okay, cool. We're good for part two. The computer-based virtual simulations, I never try and sell these virtual simulations as a replacement for good design and testing. It's really supposed to supplement that work and to help make that testing and design more targeted so you can spend the time to make parts. You can focus that on just a few good ideas, and you can filter out all those crazy ideas way ahead of the time you have to go make new parts and test them. And there's a lot of tools out there that you can work on, that you can use to work on these kinds of things. I'm going to talk about a couple that we use, but certainly that's not exclusive to everything that is out there. The main workhorse that we have, it's a software called GT Suite. It comes from a company called Gamma Technologies. And I need to be clear here because sometimes people confuse. We do not sell software. What we do is we provide the service, and this is the software that we use. A company called Gamma Technologies sells this software, and I'm not pitching this as a sales pitch for Gamma Technologies, but this is the software that we like. They're a worldwide market leader in this business. It's physics-based modeling, very stable platform. They got 200 people, I think, plus in the company that are doing development, and the customer support is really unmatched out there. Over the course of all the years that I've been doing this, I've worked with some other companies, and Gamma Technologies is great in that respect. It also allows you to integrate a lot of these multiphysics platforms, so we can build models that address the flow, acoustics, thermal, mechanical, chemistry, electrical. When you're doing EVs, you're probably going to combine electrical, some chemistry if you get down into the battery construction, certainly mechanical when it comes to the vehicle. So this allows you to incorporate a lot of those technology domains into one model. There's a lot of pre- and post-processing available. They have lots of modules that let you kind of break this up a little bit, and it couples really well to other software out there. If you want to do controls development, you can hook this into Simulink. If you want to do CFD work, you can hook it into a software like this, this is primarily the software that we use for our 3D CFD, is called Converge. Sometimes we use AVL Fire, but AVL Fire is usually a little bit better in our respect for if you're doing exhaust after treatment kind of work. Don't see a lot of that in this industry. But by and large, for the work we do, if we were going to do cylinder head or manifold work or in-cylinder combustion work, in the case of electric vehicles, if we wanted to do modeling of battery cooling, we would probably use our Converge CFD. Now, starting some of the EV basics, electric vehicles aren't just new from the last couple of years ago. The electric motor, as I discovered, it was invented back in 1831, and then shortly after that, somebody invented the first pure electric vehicle in 1832 to 1839. So they've been around a long time. They didn't really take hold for quite a while later, obviously. Back in the early 1900s, that's kind of when the ICE engines came in, and that kind of prevailed. EVs virtually disappeared in the 1930s. In one of the oil crisis in the early 70s, kind of reintroduced the concept to a lot of people, and they started looking at it again. And then some of the emission standards coming in. And then 1992 is when, by and large, the first EV made by Toyota and the Prius hybrid, that came out in 1997. In 2011, there was about 3 million hybrids sold worldwide. Everybody knows the Tesla story. Now they're upwards of 1 million electric vehicles from back in 2020, and they're kind of leading the market right now. So the point here is that this is nothing new. It's just finally gotten to the point, the technology has gotten to the point where now you can roll it out to the masses. Some of the nomenclature, you see a lot of this out there. You see XEV, or you see some of these other acronyms in there. It implies the X can mean whether it's a battery, a plug-in hybrid, a full hybrid, or a fuel cell. The battery electric hybrid is obviously it's electric only. There's no other power source in it. The plug-in, you have not only the electric motors, you also have a gasoline or a diesel engine or some kind of internal combustion engine in there only. But you can also plug it in to charge the battery. So you can get your electricity either from plugging it in or from running that secondary power source, the ICE. A hybrid electric, we call it HEV, there's no plug-in option. You're either powered by the IC engine or electric motor or a combination of both. So the IC engine has to do all the charging. Fuel cell is something that's kind of, it's out there, it's coming. This uses an electrochemical process to convert hydrogen into electricity, which powers its motors. It's fueled with compressed hydrogen that's stored on board in a tank. Beyond that, there's some other things coming. There's some new battery developments. There's some new types of lithium batteries. There's ultracapacitors. A lot of people working on that to help fill in some of these other options here. Another slide on some of this nomenclature that you might see out there in the literature when you're reading the articles is it's the P-something hybrid nomenclature. A P0 is an electric motor. It's that top picture there where you see the electric motor is connected to the IC engine through a belt on the FIAD. And this could be, you'd see this on a lot of like 48 volt systems, start gens, where that's actually the starter that runs it. P1 architecture, the electric motor is connected directly to the crankshaft. You can see the picture way over there on your right. It's in line, it's right behind the engine, but before the clutch and transmission. P2 architecture, the electric motor, it's a couple of options. It's either side attached through a belt. It's after the engine though, after the clutch. Or it's integrated between the engine and the transmission. So it can go, it's before the transmission, but you can attach it a couple of different ways. The P3 architecture or P4 architecture, the electric motor is after the transmission. And it's connected through a gear mesh. And this, if you see like wheel-mounted electric motors or axle-mounted electric motors, that would be in the P3 or P4 class. Here's just a picture of a couple of examples out there. The one on the left is all electric. The one on the right is a plug-in electric. You can see there's a lot more componentry that goes with plug-in electric hybrid vehicles, and that's why they've kind of fallen away from mainstream from an OE perspective, is because you basically have two power plants in there. And it adds a lot of cost, it adds a lot of flexibility for all of us that might have some range anxiety, because you're always going to have a backup way to get home or a backup way to charge. But it adds a significant amount of cost to the electric vehicle as a whole and complexity. You still have to certify it for emissions. The electric vehicles, there's virtually no emissions you got to worry about certifying it for. A lot more calibrations. So there's a lot more investment and cost with that. So that's really why the OEs have kind of leapfrogged that and going right to the full electric vehicle. Some of the components, the EV basics, the first thing is the battery pack. This is the energy reservoir that contains all the energy that the car will use to drive. It operates the heating and cooling and run all your other ancillary accessories. The battery management system is a computer all on its own, the BMS. It monitors and manages the condition and the operation of the battery cells during voltage. It's very important to control the temperature and the current flow. Most common, what you're going to see out there are 400 volt and 800 volt. I think downstairs in the EV room, you see some of both. I saw some 400 volts and I saw some 800 volts. There's people out there working on 1200 volt systems. That's a little farther out, because as that voltage requirement goes up, things get a little scary. We've looked at some of that on big like locomotives where, okay, they've got the infrastructure in the vehicle to be able to handle that. But it's coming. I think the voltage is probably going to keep going up for a while. These contain hundreds or even thousands of little 3 to 4 cell volt. You see, let me try what do I do with my pointer here? There it is. These big battery packs here, this is a whole big tray. It's like, I don't know, many feet by many feet big, full of thousands of these little bitty cells. That's what makes those up. And they're all connected either in parallel or in series, which is what determines your current capability and your voltage capability. And then with these models that we have, you can model them either from a detailed chemistry level or to an overall system level. The models that Varun's going to show you here in a little while, it's more of a higher level system. But if you really want to get into battery design, you have the capability in these tools to go down to the basic chemistry level. And it's really it's probably the biggest stumbling block right now in advancing EVs is the battery technology, but it's getting better and better. They're getting cheaper and cheaper. But of course, we're still restricted by right now where all the lithium comes from, and the economy of digging up all that lithium and refining it. Still takes a lot of diesel fuel to mine all that lithium to make electricity. The power inverter and converter, the batteries, it's one big bank of DC voltage. You have to convert that to AC because the motors all run on AC now. So you need a converter to do that. You also need an inverter because you have to take, when you're in regenerative braking, that means when you're braking or you're slowing down, the tires are actually generating electricity or the rotational motion to run the motor in backwards mode to backfill your battery. So you're actually taking AC power there to make DC power, so that's where you need your inverter. These are usually combined into one control unit, and they're matched to this whatever specific motor you have at the time. Just a couple of examples that Borg-Warner provides of either an integrated converter or a standalone inverter, inverters. The electric motors, obviously this is the component in the electric vehicle that transforms the electrical energy from the battery into rotational motion that drives the tires. They come in a lot of different forms. This kind of goes back to that P0 or P1, 2, 3, 4 as to which unit you have here, whether you have the drive unit is where it's at, whether it's in the axles, or in the wheels. It's probably going to be something like one of these pancake motors, or in line along the drive line. Charging, much like the access port to a gas tank, and in an internal combustion engine, the charge port location is where that's where you load your energy. The in-vehicle components include the onboard charger, OBC, and the charge port. There's different levels of EV charging. Level 1, where the vehicle charging, you're plugged in a 110 AC power. It's obviously going to be pretty slow. A little bit faster, you can go to level 2, which is a 220 AC power. And then level 3 is this DC fast charging, where the vehicle is charged using an off-board charger directly providing DC power. And there's different levels. The world really hasn't decided how it wants to commonize this. So right now it's just kind of it depends, all the vehicles are different. Tesla has its own proprietary, they're kind of like Apple where, okay, nothing else works on a Tesla. So you have to know where to go charge depending on what kind of vehicle you have, because it's going to have all the different kinds of chargers or charging ports. Hopefully, maybe SAE or somebody can come to a common standard in the future, so it can be a little bit more universal. Thermal systems, the lithium-ion batteries, which is mostly what we see now, they have a very narrow temperature operating range, and they're best kept near room temperature. It's kind of a Goldilocks thing where they don't want to be too hot, they don't want to be too cold. We all see in the news almost weekly what happens when they get too hot. The temperature management is very critical. So this thermal management system, the TMS, it can extend the life of the battery pack by cooling it while fast charging and on hot days, and even warming it up on cold days, or to prepare it for fast charging. And then this TMS can also be used to manage the heating and cooling of the vehicle cabin and the motor and the power and electronics. So you see down here, this is an example of a battery coolant heater. These pictures, these two bottom pictures here on the center and right kind of show the layout of the cooling path through the battery pack. And there's a lot that goes into that. And there are ways to model that so you can look at trying to optimize that and to make sure it's going to be adequate through the operating range. These are usually like sandwich plates that are put between the levels of the battery pack, either top and bottom, and if there's multiple levels, that they're going to go in between. Some of the electrical accessories that you need to run because you don't have an engine, a combustion engine with a crankshaft that turns things. So everything's got to be electric. So you're going to have electric AC compressor, an electric cabin heater. You'll have a DC to DC converter because you have to take that 400 or 800 volts and step it down to things that are going to run on 12 volts. And then you got to have electric brake booster, because you don't have anything to make vacuum to run vacuum brakes. So you need this high voltage junction box. They're used pretty widely to distribute the battery power to all the different accessories. So that's the end of my intro and kind of the basics of the nomenclature. Varun's going to set up his models and show you how we actually build a model using GT Suite. And then if the internet gods are working, it's going to run live, right? Okay. All right. Give us a minute to switch over computers, and we'll be right here with you. That went better than technology usually goes. All right, is he switched on now? Got it.
Hey everybody, can everybody hear me in the back okay? Awesome. Thanks Dan for the introduction, and the introduction to all these different parts is really critical. That provides context, and when I go into the model I can jump in quickly and show how we set up those models. Now when it comes to computer-aided engineering, which is not design related, there are two essential types of simulations that happen here. If I get the slide working, they will happen. No? Okay. All right, awesome. So there is 1D simulation and 3D simulation. Now this is mainly to model all the power related aspects of an EV. So you can talk about all the mechanical aspects, the electrical aspects, and the thermal aspects. There are 4 different types of simulations, whether it's 1D or 3D, that you can use a CAE tool for. One is the full vehicle, where you're modeling the entire system, right from the body, the motor, the battery, etc. They are required for drive cycle simulations. So let's say you want to model a race car going through a track. You would need to model a full vehicle. Now, if you want to understand the importance of a detailed subsystem and the impact of it on the full vehicle, let's say the HVAC system or the battery electrochemistry, then you need the next level, which is the full vehicle plus the detailed subsystem model. You can also just skip that and do a component level if all you are caring about is that particular component. It can be a motor, a battery, or it can be one of the pumps that goes into the HVAC system. All you need to do is model that at a component level. A lot of the work that's been done there is either the electrochemistry of the battery or developing controls for the motor. And then finally, you have 3D, CFD, and CHT analysis. Now that is used for battery cooling and also for cabin cooling. This slide shows some of the examples of what I've been talking about. So a full vehicle simulation could be to determine battery range or sizing the motor, sizing the battery, controls development, aerodynamics improvement, which is pretty critical in a race engine, and also weight impact. All of that can help you determine what is my range for the battery, what kind of motor I would need, etc. For the detailed subsystem, now you're looking at the impact of subsystem level on the range or the efficiency of the system. Now this can be HVAC, battery cooling, battery aging, detailed motor model, etc. And then on the component level, you have components, so e-axle development, motor controls, detailed battery modeling. And then on the 3D CFD side, I already talked about battery cell or pack thermal analysis, pump flow modeling, and cabin cooling. Now, a lot of you here would have experience as to what it takes to do testing of either the component or the motor or the battery. So to give a comparison about the time it takes to do a computer analysis, we can set up models like these in one week, and then based on that, we can do multiple simulations. So a project of a full vehicle simulation typically ranges, for us, it ranges between 1 and 4 weeks. The full vehicle and detailed subsystem, we've done 3 to 24 plus week projects. For component level, 2 to 12 weeks, and for the 3D CFD, around 2 to 8 weeks. So a lot of this is upfront work in setting up the model. But once you want the model to run, we can run a full drive cycle, let's say a FTP drive cycle or a race track. You can run that in seconds for a full vehicle type simulation. But if you have a detailed subsystem, it can still take just about 10 minutes to run. You don't break anything, you don't get anything on fire, essentially, and you can run it all the time. You're not competing for dynamo, you're not competing for test stands, you're not competing for racetrack time. It is not to supplement any kind of testing. It's just to make sure that you are pointing exactly where you want to, rather than spending 3 months doing trial and error. Even experienced trial and error, but a simulation like this, you're not breaking anything, and that's the main advantage. Also, you're getting data from a lot of other components, which you're not unless you don't have a sensor attached to that in a testing environment. So what I'm going to do is I'm going to go into a live demo. Live demo generally brings up some questions. So if you have a question, feel free to interject. And if you can, please come to the mic and I can tackle that right then and then. If I don't know anything, I'll bring Dan in as well. All right, so I should be able to go to our computer model now. All right, I think, yep. So GD Suite is the tool of choice for us. We are a 1D and 3D simulation partner for OEMs, tier ones, startups, race car teams. We don't supply this tool like Dan mentioned, but we do take advantage of it to run these types of simulations. So I'm going to share a model of a vehicle, electric vehicle, and what I'm going to do here is show you a comparison between 2 battery packs. So one battery pack will have 96 cells in series and three parallel branches, and then a battery pack which is 33 kilowatt hour, which will be 96 in series and 2 in parallel. And this is basically a good way to show what it takes to create a model like this and the kind of advantage that you can get out of it, which is where you can run this in seconds and get a comparison between 2 battery sizes. This can be translated into motor sizes. It can be translated further into heat pumps, anything that you can think of on the power generation side of an electric vehicle. Before I run the simulation, let me dive into each of these subsystems to show what we are using, the data we are using to feed these models. So this is the vehicle. So you can see there's a vehicle body, all the axles. We are modeling the tires. We are modeling the differential, which has a final drive ratio. In this case, it is 7.05. It is, the vehicle here is a truck. So we are feeding in the mass, the passenger and cargo mass. We are giving aerodynamics. So here you can see drag coefficient, frontal area. You can also use ABC coefficients, if you have it, to model the aerodynamics of the vehicle. Now this is going to determine how much power you need at the wheels for it to follow a drive cycle. To follow the drive cycle, we use a controller essentially called a driver. In the driver, depending on the type of vehicle it is and all the power generation aspects, will try to follow a drive cycle. So in this case, we are going with a USO6 for this example. And you can see this is the drive cycle it tries to follow. Now, the acceleration event will determine how much power you need based on the vehicle mass and the aerodynamics, and that is then supplied by the power generation of this model. The first thing that gives power to the wheels is going to be the motor. So here we have a map-based motor which has a maximum torque on the depletion side and a minimum torque which is used on the generation side when braking. And then you have a motor efficiency which is like an XYZ data. So you can think of it like an island of engine speed on the x-axis, the y-axis is motor torque, and then you have different efficiency numbers. This is key because this is a part of the system that you can optimize for. You can try to optimize to be in an area where you're running the motor efficiently, because that's going to use less electrical energy on the battery side. The way the motor gets power is from the battery. In this case, the way we have created the battery is by using electrochemistry, number of series cells, number of parallel cells, and then we determine the open circuit voltage for charge and discharge and internal resistance for charge and discharge for each of these single cells. So here on the x-axis you will have battery SOC, and on the y-axis you have different temperatures of the battery, as that's going to change what the open circuit voltage and resistance is going to look like. All right, so I've gone into different components of this model, and this is the way we set things up. I am skipping a few steps here, like the 12-volt battery, the DC to DC converter, and the inverter is taken care of inside the battery element as well. So I'm going to run this simulation. What you're going to see again is a comparison between two battery packs. One is a 50 kilowatt hour battery, the other is the 33 kilowatt hour, and it's going to run an electric truck. So as you can see, the simulation is running, and we are already done with probably case 1, and now we are doing case 2. So it's pretty fast simulation to run a drive cycle of an electric vehicle. What's the logical next step is to look at the results. So the first thing that you would like to know is, what is the difference in the SOC of these two battery packs? What is my range like? So as you can see, on the x-axis you have time. That is the time to run that drive cycle. On the y-axis you have state of charge, or the percentage battery that you have remaining. So with the 50 kilowatt hour motor, it's obvious that you will have more charge remaining by the end of the drive cycle. So you're going from 0.8 to about 0.72. With the 33 kilowatt hour battery, which is a smaller one, you are using a lot more energy. So you are going from 0.8 all the way down to 0.65. Now you might say that, okay, this is not bad. I can make use with a 33 kilowatt hour battery. Now we are using a USO6 drive cycle, which is 600 seconds. Imagine if you have a longer drive cycle, or you are running laps of a particular drive cycle, you will be able to use this information to determine this car is going to run X laps based on the battery size I have. And that can determine which battery you use. So the motor, this is how the drive cycle looks like. So we have a USO6 drive cycle, and I'm going to zoom in here. to show you that how with a smaller battery, the motor gets limited, and you can see that its impact on acceleration. So as you can see, the motor gets limited with a smaller battery because it can't give as much current to that motor size that you have. Now you can still size a different motor for that battery. It may not perform the same way that you want to. So here shows a difference between, on the x-axis you have time, on the y-axis you have motor speed, and you can see how the motor is not able to match up what the demand is for that smaller battery size. So again, a use case for simulation trying to evaluate what kind of motor size you want, what kind of battery size you want. You can see the same here in the brake torque of the vehicle. So let's see here. The same thing that I said in the last plot. And I'm still being at the surface level based on how much time we have. But you can see that the brake torque for that motor is getting limited here. The 33 kilowatt hour motor is getting limited because it just does not have any other current to follow what the 50 kilowatt battery is able to provide. Here's another example of that, where the 50 kilowatt hour battery is able to provide the electrical power it needs, whereas this one just gets limited for this level, and then it comes back up again. So those are the simulation results that you can get from this type of a analysis. Now, before I don't have any other demos for you, but I do have other models that I can showcase, where, like I said, we can either be a full vehicle system, just a full system, or you can have a subsystem. In this case, it's a thermal subsystem where each of these components are providing heat inputs to a cooling system and an oil system. So there are just tons of other examples and other simulations you can run to improve the engineering behind the electrical vehicle. Let's say you are a company that's trying to create a demonstration vehicle to showcase one of your components. You can use a model like this to do controls for that component and also show the impact of that component on battery range and drive cycle simulations. So in terms of a demo, that's what I had for you today. But if you have any questions, I can go into these models, or I can go dig into the results to share more about how we can take advantage of computer modeling to improve the engineering behind the electric vehicles.
Somebody's got to ask a question. You go first, right?
Can they ask us to use the mic if possible?
Right here?
Yep.
So I can be quiet, right? My name's Keith Howard with Nedra. I'll give you a task here to do something with. I've got Don Garlis' Swamp Rat 38 car sitting downstairs in there. We want to run that car to 200 miles an hour, okay? I can get you all the data, all the acquisition stuff that we need to put it really right now. And when we deal with batteries, just deal with your battery type that you're using. Obviously, we're racing with very high cobalt component batteries for that, and for people, our C rate. Cars like in Huff's car that's sitting down there, the current technology, that runs 250 C burst cells as a C rating on those to do that. So what I'd like to do is see that we can talk after this and get everybody's input here to do it. You know, I'd like to help Garlitz out. He can't make it today because of some things to do it. He was supposed to be up here today. Unfortunately, my private jet that I don't own won't get him here fast enough, and I can't get him up here and out and turn him around in the same day to Indy and be here. But I'm kind of speaking on his behalf. But what we're trying to use is use this modeling analysis to do this, because we have to size the battery pack. And our duty cycle is real easy. It's a quarter mile, okay? I'm looking between burnout and everything of a 10-second duty cycle. The car will probably run in the low 6s. at 200 miles an hour. I've got the specs on the tires. We've got the tires, the rear differential. We have the motor in there. I need to get motor data because it is a one-off DC 13-inch interpole 400-volt machine that I need to get data on. You can't do anything on your modeling unless I can give you some more data, which I'll work on. Battery cells, we're working on finalizing a deal what cells we're going to run in the car now to do that. One of your most stuff out there, if you saw down there's a Formula E car down there. It's actually a Gen 2. It's not a Gen 3 car. It's a Gen 2 car down there. The Gen 3 architecture is 900 volts, built by Williams Engineering to do that. That'll be the baddest cell that's out there for running an event to do that, because that's got to be able to handle the cooling. For anybody who doesn't understand what Formula E is, it's the all-electric version of Formula 1. Gen 3 car out there, the changes to this car this year in Gen 3 is it has no rear brakes on it. It has strictly regenerative energy braking. It has a generator on the front axle to help generate power, and it will do maybe a 350 to a 500 kilowatt 30 seconds pit stop in the middle of the race to do that, to drive technology. That's what Formula 1 does. They got more money than anybody else, right? But we're trying to use this real world tools to model this to do it. You have the tool, I have what I need to do. I need to create the solution to do that. I'll give you a great project if you want to get involved, and I can't think of anybody better in this room than anybody thinks who doesn't want to help Don Garlitz get to 200 miles an hour. Huff beat us because of COVID, and if we can make everything work right and do this, it's not public, but it's out there. My goal is to get it where I can have Garlitz and Huff race each other at side-by-side 200 mile an hour race electric at Gainesville in March. That's what we're trying to do. And to make that happen in this short period of time, I need the tools that you have to be able to do this. And that's kind of one of the things, I think that'll give you some more modeling to do that, because we've got very few pieces of the equation. Our time is short. I'm 10 seconds duty rating. I know what the motor does. I have the batteries. We know the gear ratio. We're running top fuel tires on it. You know, but nobody has a really good growth to figure what does a top fuel tire actually grow to in circumference based on what its torque profile is. So we're going to learn some interesting things about that. So that should give that, and I kind of figured that was a good way to open the discussion for where your tools can be valuable for a race team, whether you're running from the quarter mile or you're running laps, which is a neat thing. You'll see Charlie downstairs, who, if anybody hasn't been in that booth, you'll see the car just came off the racetrack. It ran the second year at 25 years of Thunderhill and finished the race. He's the only EV out there, and he finished 17th overall. So you can see what a thing looks like that. But yeah, getting data, trust me, trying to do it by the seat of your pants, anybody's race, trying to do things by the seat of your pants with no tools to see what happens, how does it feel, what does it do, is a recipe for failure and or bad things happening. The good thing is with Garlitz's car in the prior configuration, we got good data with race pack data to get some data from the previous configuration of the motor, and we knew it just wasn't going to get there, which is why we made the change. But now I've got the car leaves here on Saturday or Friday or Saturday, whenever we get Saturday, the car leaves, it'll go back to his shop in Ocala to start the project to do this. And I figured it's a good way to start the dialogue and the interest. I don't ask for money. I don't ask for this. I just find the smartest people in the room to solve a problem. And I figured that's a good way to ask a question. How's that? I get that stuff. That kind of gets everybody in the room involved in doing this to get lost. We have a problem, we have an equation to solve, and the data to do it. And that should give me the simulation for that, because I need to get you what do we need for a battery? And I can get up to 400C. I can get 400C. For people that don't understand C-rate in batteries, I'll give everybody an educational thing. C-rate, a Tesla 6C. Figure fuel flow, that's a fuel line the size of your pinky. I'll figure 400C is a fuel line that's this big, of how much fuel I can get out, how fast you can suck the energy out of a battery to do that.
In this case, I think what is critical for you is, from what I'm understanding, is getting a battery which is small enough that provides the power required at the wheels. Small enough because of low weight, less packaging issues, and then fast enough to get to your target.
Yeah, that's correct. We have to get the battery sized in what kilowatt, because we don't want to carry a lot. We've basically designed these cars and battery packs so we could run to back if we needed to. But basically, we designed to make one run with a 30-minute recharge cycle to do it. Just like fueling a top fuel car or any race car, you make a track. And the nice thing is we can drive it up to the starting line, we can do the burnout, and we can drive the car back to the pits and do all that. We don't have to have a tow vehicle. We can do all that with that. So it gives us the ability to do that. What size do we have to do that? There's a lot of efficiencies with the motor. We are in Darlitz. It'll be a DC machine. It's old school stuff. It is not AC. It will be a DC machine, which is kind of our play down there on what we're doing is DC versus AC, which is to go back, which is like Edison versus Tesla in the real world to educate people. But I think your tool can do that. I need to get you the data to put into your battery type models and what that. We'll talk after this a little bit, but I figured it always takes one person to start the conversation and see how can we turn your presentation into relative real data that can make a difference and an impact. And appreciate the time. Okay.
Yeah, thank you. And when the use case or the case study that you want to do is exactly why something like this was built. And one thing I will say is that you talked about motor data. You don't need a lot of motor data. You just need the limits. And efficiency is something that we can use either from our experience or literature out there. So that is definitely possible. Thanks for that question.
So a question on the driver profiles. How would you model or translate this to a track? So is it spatial, or how do you get that profile?
Yes, there are different ways that you can model that. So right now I showed a case where the driver is following a speed profile. But you can also have the driver follow a distance profile, and then whatever time it completes that profile in, it helps you compare between, let's say, for example, two motor types. That is following a distance profile, and you're giving it all its information. You can do that as well. Or you can, what we've also tried to do is, let's say you have a speed profile versus time. If you want to see how fast a vehicle would go, we would reduce or compress that speed profile by changing the X multiplier. So let's say right now the X multiplier is 1, we are going to make it 0.9 and see if the vehicle is being able to follow that drive cycle or not. If it is, then you can know that your vehicle is capable of running at that higher speed, because the acceleration changes if I add a multiplier to the x-axis. So there are 2 to 3 ways where you can simulate a racetrack in this environment. Thanks for that question.
What about drag coefficient of error?
Drag coefficients is an input to the vehicle, and that's what is determining, let's say, your power it requires. Now, so the question was the impact of drag coefficient on let's say, a race car. So in this case, all you need to do that comparison is, rather than comparing the two batteries, you just compare two drag coefficients. So you have, right now I have 0.29. You can have, let's say, 0.26, and it will showcase how faster your vehicle can go. Sorry, there's somebody there. Yeah.
Hey, Varun, Dan, nice job. Bernard Carr with Carmerica. So just a question about the tool. Can you model accessories? Because you had consumers in there with really just the motor, right? But can you model accessories? Because we all know, or at least we should know, there's some variability out there in the production vehicles, the BEVs today, where, our range is this, but they're not telling you that they're not consuming the whole battery in their calculation. So I wanted to know, can you include accessory, HVAC, that kind of thing in your model to really get a whole holistic story? Can you do that with this tool?
Yeah, absolutely. So there are different levels of accessories modeling. The highest level, the system level, can be as simple as, this is the amount of power I need for all my accessories, which is this case. In this case, I have 300 watts getting drained from the battery for the accessories. That's the highest level. Now you can go deeper and deeper and define each of your subsystems, and that can draw from the battery as well. Right, so I have an example of that where it's doing that. Where is it? Probably this one, the battery cooling. So this is a battery cooling model, but this is a standalone one. Sorry about that. Here we go. Right, so this is the entire HVAC system. We are modeling that as a draw on the battery of running all these different compressors for the HVAC system. So then you can go deeper and deeper as much as you want.
Thanks for clarifying that.
Yeah, thanks. All right. Any other questions? Nope. All right. Great. Thank you for your attention, guys. If you want more information about this, you can leave a card with us. You can take one of our cards, or I'll leave this slide on, which has all our contact information if you want it. You can even give us your email address if you want more information about this. Thanks for all your attention, and from Dan and my behalf, we really appreciate you coming here.